Okay, so let's consider the following example. I have a set S that consists of vectors, polynomials that sit in the vector space P2, polynomials that have degree at most 2. So my set S consists of the vector 1 minus t, the vector 1 plus t, and the vector 2t squared. And I would like to determine whether or not this is a basis for P2. And so we know that P2, that has dimension 3 because we have a standard basis, which is that consists of 3 elements, 1, t, and t squared. So any other basis for P2, now we know must have 3 elements. So here's such a set. There's no guarantee, however, that any set with 3 elements is going to be a basis for P2. We need to make sure that these 3 vectors span all of P2 and they're linearly independent. And so the next theorem, which is called the Basis Theorem, is going to help us save some time when we want to determine whether a set that contains 3 elements is going to be a basis for a vector space that we know has dimension 3, for example. So let's state the theorem. So the Basis Theorem states that if V is p-dimensional, so we know that there's some basis for V that consists of p vectors, then any linearly independent set of p vectors is automatically going to be a basis for V. So if we have a collection of p vectors that are linearly independent, then by default that's going to satisfy the condition that this set spans the entirety of the vector space V, and that's going to tell us that the set is a basis for V. And so if we look at our example with our vector space V being P2 and our set S consisting of 3 vectors, 1 minus t, 1 plus t, and 2t squared, we've got 3 elements in this set. So all I need to do is show that these 3 elements are linearly independent, and then we'll have a basis. And so for example, this first vector in set S, I can tell is linearly independent from the second vector in set S, since the first vector is not a scalar multiple of the second vector. So these two are linearly independent. And then the third vector in this set consists of a quadratic term. So there's no way that we can take a linear combination of linear polynomials and wind up with a power of a degree of 2 in our polynomial. So we know that 2t squared is linearly independent from the first 2 vectors. So I know that set S consists of 3 vectors that are all linearly independent, and thus we know that this set therefore is going to span all of P2. So this set is in a second basis that we've identified for this vector space P2. Okay, so next let's revisit this idea of matrix subspaces. So recall that given a matrix A, we can define the null space of matrix A and the column space of matrix A, where the null space of matrix A is going to be the set of all vectors, so that when we multiply A times that vector, we get the 0 vector. And recall that the column space of A is the space that is spanned by all of the column vectors of matrix A. And both the null space and the column space are subspaces. In particular, the null space of A, since we're thinking about what are vectors x that when we multiply by matrix A, we wind up with the 0 vector. These vectors x are sitting in the domain of this matrix, which is going to equal the number of columns. So any vector x that I take matrix A and multiply by is going to have the same number of entries as matrix A has columns. And the column space of matrix A is going to be a subspace of the codomain, and that's going to equal what we get in the end is going to be a vector that has the same number of rows as matrix A. And so one way that we can identify vectors, a basis for the null space and the column space, if you recall, is to take this matrix A and doing row reduction or using Python, we can write it in its reduced row echelon form, which I have up top. And now from this reduced row echelon form, the reason why this is useful this is how we often can solve the homogeneous equation AX is equal to the 0 vector. So in this case, we can set up, we can see that from the reduced row echelon form, we have two free variables, namely x2, the second column doesn't have a pivot, and x4, the fourth column does not have a pivot. So solving for x1, x3, and x5, we can write out the null space is going to be any vector that has x1 equal to -4, x2 -2, x4. X2 is free, it equals x2. X3 is equal to x4. X4 is free, so it equals x4. And we see from this last row that, or the second to last row, that x5 is going to have to equal 0. So now we can see the null space we can write out as a set that's spanned by the vector -4, 1, 0, 0, 0, and the vector -2, 0, 1, 1, 0. So therefore, we can see that the null space, since we have a basis of two vectors, is going to have dimension 2. And for the column space, recall what we can do is look at the reduced row echelon form that we get after doing row operations. And we can see here we've got 1, 2, 3 different pivot columns when we have the reduced row echelon form. So therefore, the column space of matrix A is going to be the space that is spanned by the corresponding column vectors in the original matrix. So in this case, we pick the first column of matrix A, which is 1, 3, 2, 5. The third column of matrix A, which is 0, 1, 1, 2. And then the last fifth column of matrix A, which is -1, 5, 2, 8. This spans the column space, and then you'd want to double check that this set of three vectors is linearly independent. I'll leave that for you to verify, but these three vectors are linearly independent. So therefore, we've got a basis that consists of three elements. So we would say the dimension of the column space of matrix A is 3. And so before we summarize things more generally, it's worth defining a couple of things here and looking at the connection between the dimensions of these spaces. So the dimension of a null space we call the nullity of the matrix. And the dimension of the column space we call the rank of a matrix. What we can see here is there's something significant about 2 plus 3 equaling the number of columns in this matrix. And so we're going to state this theorem on the next slide and see how we can apply it. But what we're going to claim is that when we take the sum of the dimension of the null space and the column space, we should get the number of columns in matrix A. And hopefully that makes some sense, since the dimension of the null space, that's going to equal the number of free variables that we have, which is in this case was 2. And therefore the column space was the remaining columns, which in this case was 3. And so this result is what's called the rank theorem, and we'll take a look at this on the next slide.